Hey guys, welcome back to General Chemistry. This is going to be the last video for my course in this module number 3. So this is going to complete the first half of the chapter 3. Today we're going to talk about something called quantum numbers. So quantum numbers are going to help us to locate or identify where an electron is residing around a nucleus. We can think of quantum numbers as being an address or a zip code to finding that electron. So let's run with that analogy. So quantum numbers describe the location of an electron, and it's very much like a zip code. So let's talk about how zip codes work. So zip codes are going to be 6 or 5 digit numbers that tell us exactly where we are residing in the United States. The first 2 or 3 numbers is going to put you into a particular state. So here in the state of North Carolina, we start with 27 or 28 is our zip code. When I lived in Illinois, my zip code started with 62. So it could be 60, 61, or 62. So first 2 numbers are going to put you into a particular state. The last 3 numbers in a zip code are going to put you into a particular region and a particular county, city, and maybe even a part of that city. So zip codes for Wilmington, North Carolina, they could be 28401. So that 401 is going to put me into Eastern North Carolina, into New Hanover County, and then specifically into downtown Wilmington. Okay, 28451 is going to put me into Eastern North Carolina. It's going to put me into Brunswick County and specifically Leland and Brunswick County. 28459, I believe, is the North Campus for Cape Fear Community College. So that is Pender County, Castle Hayne, and the specific part of Castle Hayne. So those last 3 numbers are just giving us more specifically to our location. Quantum numbers are going to be a set of 4 integers. So those 4 integers are going to take us closer and closer and closer to where that electron is residing or where that electron is living. Okay. So each orbital, those 3-dimensional pictures we looked at before, is a solution to the Schrodinger wave equation. And then each of those 3-dimensional pictures that we looked at are going to be identified by 4 integers, or they're going to get their own zip code. So the first integer, actually, let me go back real quick, just so you can see where we're going with this. So eventually, we'll be able to look at something like this. So I know an electron has the following address. So his address is going to be 3, 1, -1, +1/2. Okay. So by the end of this lecture, you'll know exactly where this electron is residing, what his house looks like. Does he live on the top floor? Or does he live on the bottom floor? So these 4 numbers will give you that place that that electron is residing. So the first number in that 4-digit number that you saw is the principal quantum number. There's going to be 2 things that you need to know. You're going to need to know, what does each of these quantum numbers denote or tell us? So this one tells us about the energy. And then you're also going to need to know, what are the possible values for those quantum numbers? Because eventually I'm going to give you a 4-digit zip code and say, is this a valid zip code? So you need to know what numbers are allowed. So just something to think about as you're listening. So the principal quantum number is going to characterize the energy of the electron in a particular orbital. So it's going to tell us about energy, and as that turns out, size. Remember, as we went up in energy, those pictures got bigger and bigger and bigger. That's the principal quantum number. So it's going to characterize the energy and the size of a particular orbital. The possible values for the principal quantum number can be any whole number integer. So not 0. It can be 1 or 2 or 3 or 4, so on and so forth. Theoretically, it can go up to infinity. Practically, in chemistry, this goes up to the number 7. So it can be 8 or 9 in theory, but practically we only have a number 7 in chemistry. So it determines the overall size and energy of the orbital. So the larger the value for n, the bigger the orbital is, the higher in energy it is. The smaller the number, the lower in energy. So level number 1, smallest. Level number 7, for us in chemistry, biggest. The second is the angular momentum quantum number. It is denoted by a cursive L. That's just the symbol that they use. The angular momentum quantum number is going to tell us the shape of the orbital. Okay? So the angular momentum quantum number is going to tell us, is it a sphere? Does it have 2 lobes? Does it have 4 lobes? Is it a donut? Does it have 8 lobes? So the principal quantum number is going to tell us the shape of the house that the electrons live in. The angular momentum quantum number, there's a range of possibilities. There's options for the angular momentum quantum number. So the values range from 0 to n-1. So on the first slide, I put up a series of numbers for you. So my series of numbers started with the number 3. So let's use that as an example. The first number is the principal quantum number. That was n equals 3. Now let's talk about the angular momentum quantum number. So this can be a range from 0 to up to n-3. So for this example, the options are 0 or 1 or 2. Okay, so n-1, 3 minus 1 is 2. So this electron, if an electron was in that third energy level, he would have his choice of living in a 0, a 1, or a 2 shape orbital. Okay. But when I was looking at the shapes of the orbitals in the last lecture, did I use numbers like a 0 is a sphere, a 1 is a double lobe? What did I use? I used the letters, right? So just a kind of an added piece, an extra little bonus knowledge that you'll have to have. 0 stands for an s orbital, and that was our spherical orbital, right? When the value is 1, that's a p orbital, right? That double lobe one. And when the value is 2, that's a d orbital. And when the value is 3, that's an f orbital. The f was the one that had 7 different ways, right? So when we are in the third energy level, an electron kind of has a choice. Is it going to live in an s orbital, a sphere? Is it going to live in a p orbital, a 1? Or is it going to live in a d orbital, a 2? Kind of gets to choose, right? The magnetic quantum number is denoted with a capital M and a lowercase l, or a subscript L. The magnetic quantum number is going to define the orientation in space. Okay. So this is where I was talking about a sphere. There's only one way to orient it in space. A p orbital, you can orient it up and down, left and right, coming out at you, going back into the paper. D, there was 5 different ways. So the 4 lobes and then the donut one. So this is going to be that orientation in space. How many different ways can we make this 3-dimensional picture in space? This is also going to be arranged. Since there are multiple ways to depict these in space, we're going to have multiple options for the value. So let's rock and roll with our example. So we decided that n equals 3, we said that L could be one of these possibilities. But in order to move on, we have to pick an L. So we have to say, I choose a p orbital. So that is completely arbitrary, subjective. I just picked that for the purpose of demonstration. So I'm going to say our electron lives in a p orbital. Okay. Now that I have defined L equals 1, I chose that. Now we can talk about what the magnetic quantum number is. So the magnetic quantum number is also a range. There are also options here. And it's going to be a range from positive L to negative L, making sure we hit 0 in the middle. So if our L value is 1, our options for this would be positive 1, 0, negative 1. Those are their possible values that it could be. How many different ways did I say you could orient a p orbital in space? 3 different ways. 1, 2, 3. And how many options are there for the magnetic quantum number? 1, 2, 3. Not a coincidence. That absolutely is the connection between these two. Okay. So in other words, once this electron has decided to reside in a p orbital, I picked the p orbital. He could live in maybe the positive 1 version. So that's where the lobes are side to side. Or he could live in the 0 version. Maybe that's where the lobes are going up and going down. Or he could live in the negative 1 version. That's when the lobes are coming out at you and going back into the screen. So he has a choice as to which orientation he wants to live in. He can pick any of those 3. The last quantum number is the spin magnetic quantum number. So this indicates the spin of the electron as it resides in that orbital. Okay. You don't need to know much more about the spin magnetic number other than the 2 possible values are positive 1/2 or negative 1/2. So I like to think of these orbitals as duplexes. So in every single orbital and every single picture that we see, each of these are a duplex. Up to 2 electrons can live in these orbitals. Okay. So the spin magnetic maybe says that this electron is living on the top floor, and this electron is living on the bottom floor. Okay. So all you need to know is spin magnetic can either be a positive 1/2 or a negative 1/2. Those are the only options. So I gave you the following address at the top. I don't remember if I did positive or negative 1/2. We're going to do positive. Okay. So now we know where this electron resides. He resides in the 3rd energy level, maybe the 3rd floor of a complex. Okay. So he lives in the 3rd energy level. He chose to live in a p orbital. Okay, so when L equals 1, that's a p orbital. So he chose to live in the double-lobed orbital. Then he chose, I want to live in the orbital that was coming into the screen and going out of the screen. So if I click back, maybe he chose to live in that one. Okay. And then as he chose to live in that one, he said, you know what? I'm going to live on the top floor. Somebody else could live on the bottom floor. That's fine. I'm going to live on the top floor. So now we understand the address or the location of this particular electron. Okay. So here's a good summary of the quantum numbers. So one of the skills that you're going to need in this class is taking this very complex information and the scribbled notes that you're probably taking and organizing your thoughts. So in this table is one way that I have organized my thoughts on this subject. So you can use this to help you organize, or even better, you can create your own. This is also another example of organizing thoughts. So I looked at this table at one point and I was like, wow, that makes no sense to me. And I had another student that looked at it and they're like, that's an amazing table. That makes so much sense. So I offer it. So each person has their way of organizing information. This is another way that information can be organized. Okay. The last thing I want to leave you with. Miss Madge, you just showed me spheres and donuts and double lobes and 4 lobes and 8 lobes. And this is the cloud that electrons reside in. And why do atoms always look like a sphere if there's these crazy things going on? What happens as an atom builds is these orbitals superimpose on one another. So the first house, and we'll learn this in the next one, the first house that gets filled is a sphere. And then the next house that gets filled is a bigger sphere. And the next house is the up and down lobe and the side to side lobe and the coming out at you and going back in lobe. And the next one is a bigger sphere. And then a bigger lobe and a side to side and a coming out at you going back in. And then we get the 4 lobes and we keep stacking those on each other. But what we find is as all of these orbitals stack on one another, the general outcome is a spherical shape. So here it's like tying a bunch of balloons together. And what they end up looking like is a spherical shape in the end. Okay? So that's important to understand. These orbitals don't exist or live separately like an apartment complex. These orbitals stack and superimpose on one another. So as we get a bigger atom, we stack and stack and stack and stack and stack, and the atom gets bigger and bigger and bigger and bigger. That is your introduction to quantum numbers. I hope you guys found this information helpful.